So this is an update on a project I've been working on off and on for probably about a year and a half or so. I personally enjoy working on the amateur satellites, but it can be difficult to aim an antenna, make tuning adjustments for Doppler shift, and keep track of contents all at the same time. So I was looking for a simple, small ASL rotor for my handheld aero antenna, and I stumbled across the SARC project, but unfortunately it had been discontinued, and no longer supported. I believe I reached out to them, asked for their source code because I think theirs was based on a Raspberry Pi as well, and got no response, and their website now indicates that much. Now I'm a Mac user, so MacDoppler is my program of choice for satellite tracking and tuning info. In the rotator controller settings with MacDoppler, you can actually set it up to have it broadcast on your network via UDP packet, the azimuth and elevation information, as well as tuning info for your Doppler shift, which makes it really handy, and it can be read by other devices or programs that are able to receive those UDP packets and decode them. When you download MacDoppler, it actually includes, there's an extras folder, and it comes with a UDP reader, so you can actually UDP listener is what it's called, so that you can actually see the packets that are being sent out and the decoded information in them. My original plan was to use an Arduino with an Ethernet shield and a couple of EasyDriver motor drivers, but unfortunately the code came quite overwhelming. I'm not a programmer. I've dabbled with Arduino, I've got some books on it, and generally I was trying to cobble together some code snippets from here and there to try and make things work. But I would get one thing working, it would break another thing, and I could really never get the azimuth and the elevation to work correctly together while reading the UDP packets. So I decided to scrap it. It's one of the reasons why this project took so long. I'd make some progress, run into some hurdles, put it away, take a break, pull it back out, get back on it, and then try again until I hit a point where, again, I'd hit another roadblock. Eventually I discovered Python and figured I'd give that a try with a Raspberry Pi. I've got a few of those hanging around, as I'm sure many amateur radio enthusiasts do. I got a Raspberry Pi 3B, used an Adafruit motor driver hat, as well as a PiTFT display. Since all that stuff was meant to work together with the Pi, it made wiring simple. I just needed to connect up the two stepper motors. And the nice thing was the PiTFT also gave me 4 buttons to work with. Gave me a lot more flexibility in how I intended to use the whole setup. It still took some time to get the Python code working correctly, as again, I am not a programmer, but books, internet, and now the advent of ChatGPT and AI did help get everything together, but it still took time, still many hiccups. You really need to know how to prompt the AI, as well as see kind of the logic of what is going on in it. There were many cases where it did something unintentional. One of them is error tracking, which I'll get into a little bit later. But it did take some effort to, even with the help of AI, to get things working. So right now I'm SSH'd into the Raspberry Pi, and we can see the UDP packets coming in and being decoded correctly. Right now button 1 is to start tracking. Button 2 will set the home position after it's manually pointed. So you have to set this up pointing 0 degrees elevation and 0 degrees north. And button 3 will release the motors so that they can be moved manually. Once you start tracking, the motors will lock and hold. And then button 4 will exit the program. But during testing, it could be challenging to see how well the motors were tracking, as it all depended on what satellites were in range, how good a pass it was, how high above the horizon. So I ended up writing another Python script which would broadcast the same azimuth and elevation information in the same manner as MacDoppler. I simply set it up to do a complete 360-degree circle on the azimuth, with each movement being a random number of degrees between 2 and 6.9. And since the elevation should never be more than 90 degrees straight up overhead, I made a similar routine. However, once it would hit 90 degrees, it would then start decreasing until it hit 0 again, and then start increasing until the azimuth motor made its full 360-degree revolution. I did modify the elevation so that it was a random number between 2 degrees and 4.9 degrees. just to give it a little bit finer steps. Making sure there were plenty of movements was critical because the motors take 200 steps to do the full 360 degrees. So that's about 1.8 degrees for each step. And I quickly found that errors, rounding errors because of this, added up and could make the azimuth especially out by 10 degrees or more depending on the type of pass. So I had to modify to track those rounding errors and then add them back in so that to try and keep the azimuth and elevation readings accurate. And as you should see in the terminal window, the reported degrees in the terminal, they're pretty close, if not bang on, to what the motors are actually pointing to. It's a little bit hard to see the motors in that view, but it's definitely a lot better than how I started with, and is usable. I've tested it numerous times through numerous scripts, and to me it is accurate. It would be accurate enough to track a satellite and be able to make some good contacts. Next step for this project will be to implement the PiTFT screen so that I won't need to SSH into it or an external display. I will probably have the Raspberry Pi boot up and start the script automatically, and then I can use the 4 push buttons as required to start, stop tracking, zeroize the motors, or exit the script completely. I'm also going to have to figure out how to fabricate a mount for the motors and the antennas, which I'll likely put on top of a camera tripod, make it nice and portable. But that'll be kind of the next step to figure out that part of it and get it mounted and work. It's been a great project and obviously still ongoing. It is not completely finished, but I think I've got the hard logic part figured out and working. It's one of the reasons why I love amateur radio stuff so much and why I wanted to share it, is I learn and continually learning in the amateur radio space. So lots of fun. Thanks for watching. This is VA3 ZTF Clear.